All right, so I think we're live. Get this going here. So hello and welcome. Oh boy, I want to take some time, think about this question a little bit more. Yeah, there was a little bit about Fenwick trees. Excuse me, and I think I understand. Like it's basically a version of interval trees, and basically my thinking is like, okay, I think I could solve this problem, or at least I know enough about data structures to solve this problem, if that makes sense. So I want to try to solve this problem in n log n time. I'm not entirely sure like what's gonna happen here, if that makes sense. Let me pull up Leetcode. I updated my machine, so I updated Windows, so I don't know. I don't know. It's not that I don't know. I have to sign in. That's what it is. So forgive me. I didn't think about that before I started running the camera. But here's the problem. Like I don't actually have a solution to the problem. Like that. That's always the right. Like you need to think about a problem and get the solution before you can program it. Right. Like it's not. You can't just conjure up a program or a solution out of nothing. I mean, you gotta think. I mean, you think about it, right? It's sort of like conjuring it up, but let me see. Okay, we should be able to take a look at the problems now, right? So yeah. So we'll go back to the problem. Read it again. We'll think about it some more. Also, I could do a quick humble brag. I got a few hundred problems under my belt now. Still not a third of the way there though. Still like pretty far off from a third. Here we go. I can scroll through all the. Oh, that's a new question. Oh, I missed one. I have to come back to that one. Oh yeah, there's a few of them. Huh. Interesting. Didn't realize I missed these problems. There's a couple that I missed. Should go 100 per page. There we go. There you go. So this one. This is the one. Oh no! My solution is gone. The reason my solution is gone is because that's fine. We come up with another one. The reason my solution is gone is because the local cache was cleared. I don't know when or why that happened recently, but basically the cache on the browser would store. The cache on the browser would store a. The cache on the browser would store that information. I guess it would be like a cookie. So there's like a local sort of a cookie on the browser. I guess a cookie on the browser that would be able to reload the code that was there. So that's gone. It's gone. We are given an array of people, which are the attributes of some people in a queue. Excuse me, not necessarily in order. Each people of I equals h sub I. K sub I represents the ith person of height h sub I with exactly k sub I other people in front who have height greater than or equal to h sub I. Reconstruct and return the queue that is represented by the input array people. The returned queue should be formatted as an array queue, where q of j is equal to h of j, k of j, are the attributes, should be R I think, or Q of j are the attributes of the jth person in the queue. Q of 0 is the person at the front of the queue. So basically you have a description of a queue as a list of people, and they have two numbers, a height and a k value. K value means that the number of people in a hypothetical queue that are in front of this person have a height that's at least the height of that person. That's how many there are is k. So what they're suggesting is rearrange this list of people such that they're all in their correct positions in the queue. And so one way of doing that is to actually take an approach like this. So we can do a copy of the array. We can sort with a special sorting algorithm, describe in a moment. Or yeah, I'll explain in a second. We can use a special sort, not a sorting algorithm, but a special sorting operator, we'll say, where we say a of 0, we want the largest heights to be on the left side. So we'll sort, and the heights are the first value. Or, so if that's not true, they could be, or if the height is equal, then we want to sort by the k value, which is the second value, and that's going to be sorted in increasing order. So the heights will be sorted in decreasing order, and then for each section of heights that are the same, that portion will be sorted in increasing order. And the reason for that should be clear that well, I shouldn't say it's clear. I'll explain in a second why we do it this way. And what we're going to do is with that, we're going to sort our list that way, and then we're going to insert each person into our return vector. Actually, I'll do it this way. Our result vector. What we're going to do is can I do it this way? I might be able to, I'm not sure. I'll explain in a second what we're doing here. Does it work? It does. Okay. Solved it. So this is obviously I've more or less memorized the solution at this point because I've gone over it enough. It's kind of fresh in my memory. What we're going to do is say, okay, so we perform this sort, and in our result vector, we're going to take each person from that list, from that queue, left to right, that list of that vector of people. And we're going to insert them into our results, but at a particular spot. So we're actually going to put it at the k-valued index. And what's going to happen is, because we're inserting the largest height first, clearly each element is inserted sort of one by one, and at that point, because everything to the left is always going to be at least the same height. So you must have the k values increasing from left to right in that case. Then when you look at the next set of numbers, everything again in the array is going to be at least the same height. So everything to the left is going to count as a value that you're looking for. And so again, the same condition holds where actually the k value is exactly the index that you want to insert that value at that person at in the queue. Note that all the values that you're adding after, all the people that you're putting into the queue after it, their heights are less than what you've already put in, so they don't change the relative positions as you're going. So it's a very clever approach to this problem. I think it's great. However, the problem is, I believe, so this is quadratic time complexity. The reason for that is that this insertion is basically every time you insert a person into the queue, all of the people to the right of the queue, you have to increase their index, increase where they are in the array, and shift them over to the right. So what I would like to do is basically somehow come up with a tree data structure of some kind where I can insert each person into the tree, and they'll have some index that they represent. And then when you add a person at a particular index, all of the nodes in the other indices that are greater increase in value in terms of their index. And my thinking here was some kind of a self-balancing tree that basically you would insert into a particular index that you want your node to be at, and then all the tree would kind of shift somewhat such that all of the other indices to the right increase in value, or they all get shifted down further to the right. Now, I don't really know how to do that, quite frankly. I'm not entirely sure. I want to maybe come up with an example and try to think up a tree and some insertions I can do on a tree. Like, let's actually use this example, right? So we'll put it here, and then we can actually print the people, right? Well, actually, let's not do it that way. We can sort it by hand. It's fine. So just to show that we do have the solution, but or I have I understand the solution. It's just I don't know. Also, there is a thing here before I dig into that. Wondering if this is kind of because of const auto reference. I think this creates a new vector to insert, which is kind of interesting. Not sure that really matters one way or the other. But there's just sort of a lot of copying going on, I guess. You could alternatively do this, and I think it'll be a little bit faster if you do it this way. Not much faster, but slightly faster. Use a little bit less memory. This actually destroys the previous vector in the sense that it modifies it here, and then it's permanently modified after that. But if you do this, then it copies it, and then the thing that you modify is basically a local variable. So yeah, that's why we have better memory and better runtime. If we do it this way, then it'll take more memory and have more runtime. Not too much more, but a little bit more. It's interesting that the runtime is almost the same. Yeah, it's almost the same runtime, but you can see it's significantly different for the memory, right? Almost a full megabyte. But anyway, that's not really the most important thing. All right, so the thing that we're interested in is, okay, yeah, so 7.1, delete this 7.1. And we said 6 comes next. Oh, you know what? Yeah, let's do it this way. Let's do it piece by piece. 6.1. And then we're actually performing an insertion sort by hand. Believe it or not. So we're finding the correct node to place at each step and swapping it. I'm going left to right. 7707161505244, right? So this is ultimately, after our sort, what we'd end up with. Now we're kind of like at peace with using the overhead insertion time, or rather the overhead sorting time. We'll just say we're at peace with that. So now we want to figure out a way to insert these into our data structure, into our tree, in a way, insert these nodes into the tree in a way that allows us to excuse me, I'm just, don't mind me. Allows us to insert the nodes into the positions we want in logarithmic time, and also push the other nodes that are already in there, basically increase the index after reading the in-order traversal of the tree. That's what we're gonna go for. That's what we're aiming for. Is it possible? I don't know. Can we do it? I don't know. We'll tinker a little bit and see if we find out. So clearly it works for 7.0 if it's empty, that goes to the head. 7.1 has the same value as 7, has a larger k value. So actually no. So we want to put it at index 1. So the head would say is not necessarily index 1. Like we don't necessarily know what index it is, but for now it's index 0, right? And now we want to put 7.1 at index 1, so it's got to go to the right, right? So now it's 0, 1. Okay. Now we have 6.1. We want to put it at index 1, so we would see. That's the thing that's tricky. Like, why wouldn't? Okay, so we want to insert 6.1. So let me do this. We want to insert this to 6.1. So let's put 7.0 as a child of 7.1, which is currently 1. Because you could do it this way too. Like maybe this is better. Maybe each time you add a node, you actually want to shift the tree slightly to the side. Does that make sense? So now the in-order traversal is still what we want, from left to right. But now we can put 6.1 in and swap it with 1. So now it's at index 2, and now we can swap, right? And really the key is, I guess, we want to maintain a relatively balanced tree and also be able to get our nodes into the right spot. Like it seems plausible, right? Like it seems like it's doable at first glance. Like there's got to be some way to do this, right? If there's a way to have balanced trees in the first place, like there's a kind of a rotation that we do here. And then now we say, okay, 5.0, want to go to index 0. So we would say I don't know what you'd do here. I guess you'd put 5.0 all the way to the left. So I think you, yeah, well, I don't know. Truthfully, I don't know. And because you don't just want to keep, you want to rebalance each time, right? Like, because you don't just want to keep pushing nodes to the right or to the left, right? Like you could do that, but it won't be balanced, and then it'll be expensive to push the nodes in. Something like that. I don't know. I don't know what I'm doing. Just guessing here. So if you did this, certainly this would automatically update all of these indices, right? Whereas this didn't have an index before, but now it has index 0, 1, 2, and 3, right? I don't know. Do you move this at all? I don't think so. It's where it's supposed to be. Okay, I guess. I don't know. Sure. What about the next one? Let me. I'm also somewhat concerned that this approach I'm taking here won't actually give me what I'm looking for. Somewhat concerned that this approach that I'm taking won't actually give me somewhat concerned that this approach that I'm taking won't actually give me a reasonable algorithm. In other words, like I can eyeball what should happen step by step, but algorithmically, I'm not sure if I'll actually get something that's like feasible. All right, so 5070 70 6171. Okay, now we have 52. So the spot we want to insert in is here at the head. Now, how do we know that that's the second spot also, right? Like that's another question. Like this is also assuming we even know where to insert the nodes in the first place in the tree, and then we know where to put the nodes that we inserted afterwards. See, that's a good question. I don't actually know. How would I know that this is the second? Well, I guess if you know how many nodes there are, the in-order traversal has a very clear. Excuse me. It's only 4 nodes, right? So you wouldn't have to call the in-order traversal each time, but you would know where the indices are for each node. So you don't necessarily know that either, because the tree, you don't necessarily know how it's balanced. You know it's balanced, but you don't necessarily know how. How do you know this root node is 2? I guess you could maybe keep the size of each tree on the left and the right, if that makes sense. So as part of the tree, you can keep the number of nodes beneath that particular node, and that way you kind of always know the indices. And then you can do it that way. So in logarithmic time, you can figure out which node where you want to place this. So this is the node we want to replace, and we basically always want to shift everything to the right. So we would end up with, that's maybe one way we can do it. So shifting it to the right would mean you put the node there, relabel everything. Really don't have to relabel it. You would just recalculate how many nodes are on the left subtree, how many nodes on the right subtree for this node and all of its parents, right? Actually, before I do any of that, what I want to do is copy these things. It's 5.2. Look at that. Looks like a giant potato. Maybe not. So much for a circle. Alright. They kind of all look like potatoes, but somewhat deformed potatoes. Very nice. So, okay. Fair enough, I suppose. Now what? So now we want to say, okay, so that's 5, 0, 5, 2, 4, 4. All right. So we said before, just by keeping track at each node and every node, what the number of nodes are in that particular subtree, we can figure out what the index is, like which node is a particular index. Basically, it's the subtree with that. Yeah, well, that algorithm is, I guess, somewhat tricky. You probably basically decide to go left or right depending on how many nodes are on the left side, how many nodes are on the right side, and you'd want to. That's not too hard. I mean, you can do it. It's a little tricky because it's not exactly a left and right thing, because you want to add the number of nodes from the left subtree to figure out how many nodes are to the left of a particular node in the right subtree, if that makes sense. So you got to somewhat keep track of how many nodes you've already seen recursively, but that's not too bad. You just do a pre-order traversal or a post-order traversal, meaning you check the left subtree. If you found the index, then you stop. If you didn't, then you would check the. Actually, I guess it is an in-order traversal. Yeah, you check the left subtree. If you found it, then you're done. If not, then you check the root node to see if that's the node you're looking for, using the number of things on the left side. And then if that's not it, then you iterate on the right subtree and include the number of nodes you've already seen so far in the calculation for the index, right? And then you can traverse that way to find which node to replace. But here we are. So 4, 4. This is the 6th node, and we would say 0. We have 2 nodes on the left side, so that's 0, 1, index 0, 1, which is we're looking for index 4. This is index 2, which is we're looking for 4. This is 3, which we're looking for 4, right? This would be nothing over here. And then finally, this is index 4, which is what we're looking for. And now here's kind of the problem that I was describing, is that we sort of run into issues where it's not necessarily logarithmic time if our tree doesn't stay balanced. If you'll notice, like we could just keep adding and adding nodes, but it would eventually take linear time to find which index to add it, which node to swap with, and also it would take linear time to actually perform that swap. Well, just to find the node and then perform the swap is sort of constant time, but it would be linear time overall to perform each operation, which there's a linear number of them, so you have quadratic time complexity rather than n log n. So we want to figure out a way to make sure that the tree is balanced. But in any case, we would say, okay, so we want to replace this node, so we would take this parent node, take this right child, maybe take a temporary pointer, point it here, take this right child, point it to 4, 4, and then make the right node a 4, 4, the 7, 1, using the make that right node a parent node using the make the new node the new head of that right subtree, and take that head, that current head of that right subtree, make that a right child. So now this would be, and we could do that every time, really. That would work if we did it every time. However, that would give us something that looks, you know, basically like a, that would give us something that looks like a line, a straight line almost. Like we're not running any routines in between to actually keep the tree balanced, which is kind of the issue. Like we have to make sure this is a balanced tree, but still maintain the same order that it's in. So I guess you can call a rebalancing routine. Now, I guess that means that if for every subtree that, so keeping balanced is, I don't know, like I don't actually know what to do to keep the tree balanced and keep the same in order traversal. Like that's a pretty interesting question. If we could do that efficiently, as you know, as we add elements, that would be really good. I think what you can do is not just make this node the parent of this, but in fact make both this node and its parent, if this is it should be a right, assuming there's a right subtree node, make both the parent and the right subtree children of this new node. So it would look like 5 0, oops, 7 0, 5 2, 4 4, 6 1, and 7 1. Yeah. Because 4 4 is to the right of 6 1, which it still is, and then 7 1 is to the right of 4 4, which it still is, and that keeps us balanced if we do that. Now, what would that look like if we did that for all 6 nodes? Yes, that basically, assuming the index we're looking for is a right subtree of someone. Now, if it's not a right subtree, then I'm not sure what to do exactly. But I think that's a good idea to do that swap if it's a right subtree. And how do you check if it's a right subtree? I guess when you search for it, when you find it, you would also want to keep track of that property. You can do that in tandem, I think. When you search for the interval for the right node, also figure out if it's a left subtree or not. If it's a left subtree, let's say we want to add a node here to the right, and it's going to be, when you read this, it goes here, here. It actually does here, here, left subtree first, this node, the right subtree, this node, the right subtree. So what would you do? You would do one this way, the left subtree is null, middle, right subtree up here. So yeah, adding that to the right subtree does maintain that, and all of these are to the right, as long as it's in this right subtree. Only problem is, yeah, well, once you add the node to a right subtree, then you have that thing again where you would swap this, right? So if you did like, call this like alpha, some node, and then you had some beta to add. Right, so if you added, if beta was supposed to go in the right subtree for alpha, to the right of alpha, then you'd want to swap 6 1 to make that make both of these things children of, I don't know, how do we do it? Yeah, both of these things children of this new node, right? Because everything ends up being to the right. Not that everything ends up being to the right, but parent is still to the left. Just gonna move this. Okay. Alrighty. So gotcha. So yeah, you can now make this parent a left subtree. And I guess that would keep things relatively balanced. The problem with that though is like, what if you, like, this doesn't guarantee the tree being balanced, you know, doing this operation as described. If you take, you know, if it's a left subtree, then you add the node. If it's a right subtree, then you shift the parent down a level. The right subtree becomes a child of the new node. Let me lay down for a minute. I want to think about this. Also, forgot that I had that in there, so you were hearing noise this whole time. Excuse me. I don't know how much longer I'm going to be thinking about this. Maybe another 20 minutes. Just kind of pondering. Yeah, I don't have. Oh, excuse me. Oh, excuse me. I don't have. What was I saying? I don't have. Yeah, I completely forgot what I was saying. Yeah, that's not necessarily enough to prove that the tree will always be balanced if we do those things. In fact, we may be able to show a counterexample where the tree won't be balanced if we do those things. And so then we need a stronger condition and a stronger response, right? A stronger condition and response to a stronger condition and response to, what was I saying? A stronger condition and response to adding new nodes when the tree might be unbalanced. Excuse me. I don't know, man. I don't know. How do we? Huh. I gotta think about this here. I forgot what I was doing. I forgot how. Just sorry, it's something on my mind. Just kind of distracted. Um. So. Hmm. Excuse me. I'm still thinking, pondering here. If sorry, excuse me. Hmm. How do we ensure that this tree is balanced? It basically means that each subtree. How do we even check that a tree is balanced? I want to say the left subtree for the root node, the left subtree and the right subtree have to have the same number. They don't have to have the same number of nodes. That's not true. I think it means that every leaf node is at the same depth or one depth higher than the others, one depth lower. I think that's what it means, that every leaf node is either the same depth or at most a difference of 1 between the depths of any other leaf node. Yeah, I think that's what makes it balanced. Yeah. And yeah, that's fine. That's perfect. That's perfect. So in order to keep that condition, what could happen? Well, we add a node, and right. So the node that we just described, this node being added. Oh yeah, it's a really easy way to break this condition is we keep adding nodes to the left subtree, and then we just have a big line. There you go. That's an easy counterexample. Duh. Of course. Duh. Also, forgive me. I don't know why I'm so tired. I'm just really sleepy today. Yeah, we just keep adding those nodes to the left subtree, then we'll have break that condition. So how about well, I guess we would want to keep track of the maximum depth, and if we exceed that maximum depth by more than one node, then we've got to do something about it. Now, what I think you can do is if we add our node to a left subtree, then we can take the root node, the parent, and okay, this is what we can do. If it's a left subtree, then the parent can be made. The parent could be made to be at the same level as this left subtree by making that parent a right child of its parent node. Now, let's say it's already a right child of, So I want to say there are 4 different cases, right? So added a left subtree to a node that's already a left subtree. Added a left subtree to a node that's already a right subtree, or rather, added a node to a left subtree that's added a node to a left subtree. Added a node to the left subtree. Added a node to the left child of a left subtree. Added a node to the left child of a right subtree. Added a node to the right that's a right child of a left subtree, and added a node that's a right child to a right subtree. There we go. That's what I want to say. Those 4 different cases, I want to say that there are manipulations you can make such that if the depth condition that you're looking for is exceeded. So it's not the maximum depth that you're looking for. It's actually, there's a maximum depth, and then there's a depth of less than 1. And if there are any nodes with 1 less than the maximum depth, then you've exceeded the limit. So it's kind of special. It's not exactly exceeding the max depth. It's just, where is this node being added such that so that's kind of a problem though, right? Because if it was as simple as just, I think it's actually going to be more complicated than what I'm doing here, because yeah, you basically, in all 4 cases, you want to have some operation you can do that reduces the depth. However, the problem is it reduces the depth of the node you just added. The problem, though, is that you could add a whole bunch of things to one side of a tree, and simply performing that operation isn't going to, like, I guess you won't be able to do that operation at some point, something like that, or even if you perform that operation, it's not enough. So I want to say, actually, then there's probably a kind of a cascading effect you've got to do then of things shifting things, and that should ultimately take logarithmic time, and I guess that's ultimately what we're talking about when it comes to keeping things balanced. Now, the question is, can I just go ahead and take a look at what red-black trees do and do that and not have to worry about all of this? Because I'm thinking that the cascading thing you do is probably something you do with regard to red-black trees. Yeah, it's probably the same kind of thing. It's probably like a red-black tree implementation kind of a thing. Layer the red-black tree principles on top of the index searching thing, and then should be able to do that. So we'll take a look at red-black trees in a minute, I guess, briefly, before we go. I'll probably come back to this problem again. But if we think about it, then actually the rotations that we make, we probably could recognize a way that shifts the nodes into the correct positions. I want to say something like, so there's like the maximum depth, and there's 1 less than that. And if there are any nodes that still have that depth, what less than 1 depth, and then you try to add a node and it's greater than the max depth, then you've got to do some shifting. So, like, let's say it's a left child of the left subtree.
then you can shift you can make the parent of the left subtree a right child of the left subtree, right? So basically make that the parent, swap the parent. Now the problem with that though is that what if this left subtree, now I guess it necessarily can't have a child on the right subtree, because then we would have already violated that condition, right? So yeah, so we can assume that actually that condition is not violated. So it doesn't have a right child. Okay, I guess that's fine. So yeah, then we can make the parent a right child, and now, but here's the problem with that though, right? Okay, so it doesn't have a right child, but the parent has a right child, and now even though you've shifted this, the node that you've inserted is now the depth is decreased by 1. The right child of the parent, its depth has now increased. And in fact, so let's see this parent. So there's the new node is at, let's call m plus 1. The left subtree is at m, and then the parent of the left subtree is m minus 1. Now the parent of the right subtree of the parent now becomes m depth m, as well as the new inserted node is at depth m, and the left subtree is now at depth m minus 1. Any children of that parent node, those all have increased their depth by 1, and you could, since that was at depth m minus 1, you could have had a child at depth m. You could not have any children at depth m plus 1 though, because you would have had the same problem. But you could be at m, and then now that is now at m plus 1, which is an issue. So if that has a child, then actually you want to perform the same operation again on the, perform a similar operation. The problem here though is that at this point you can't assume that there are available children nodes, I guess, if that makes sense. So there must be, so in this case we know there's a left child, so when we do a right child of a left subtree or a right child of a right subtree, it could be either one, what operations we perform, we cannot assume that the other subtree is empty. So being a right child, the left child would be empty, and then and then what did I say it was? It's a left child, right child, right child of a left subtree, and it's not empty. The problem is that before you perform this operation, you actually want to shift that child somewhere else. I think somewhere to the right, which I guess would involve making it a child of. You can actually make that a parent. Excuse me, that could be its own subtree too. So there's pretty significant changes that you would need to make, I guess, to balance this tree. Interesting. I'll just close my eyes for a minute or two.
Oh man. Oh, here's the timer. Yeah, probably should stop there. So I don't know. I didn't really come up with a good solution to this. I probably should look at red-black trees and how they keep balanced, because they basically keep the same general structure. Yeah, I don't know, man. Actually, self-balancing trees are kind of interesting. I pretty much need a form of a self-balancing tree, which I haven't really studied that too much. Truth be told, what am I doing here? I want to do this and that. 1, 2, 1, 2. What am I doing? This one is up. Sine wave, cosine wave. Hold on. Yeah, let me get going. What I want to do, sine wave, negative sine wave. I don't know. Anyway, what I want to say is, after scratching my face, yeah, self-balancing trees, I think it might be kind of a tricky thing. Basically, I think I need an implementation of a self-balancing tree. However, the thing about this is, like, I don't know much about self-balancing trees. Probably if I learn more about it, then I'll get a better sense of how it's done. I want to say there's probably is a way to, I could probably, if I thought about it for a while, I could probably think up a way to, I guess, create a form of a self-balancing tree. I think about what operations might need to be done to keep this balanced when adding one of these nodes, something like that, to a tree that's already balanced, to make sure that stays balanced after adding a node. I want to say something like if there are too many nodes on one side, then you'd have this kind of like cascading upwards thing going on, and then this would replace the root, but then you need to put that root node somewhere. So I guess you would find a place in the right subtree to insert it, which is also a self-balancing subtree, right? And then so once you insert that node into the self-balancing right subtree, that'll shift the nodes around until that's also self-balanced. I want to say something like that. Like there's a way, basically, if you can't fit the node in the left subtree, then it either replaces the root or actually, yeah, probably would cascade the changes up to the root, and then that would cause, then you'd need to insert the node into the right subtree, and then that's self-balancing also. So then that would, it's sort of like recursively would also work. I want to say there's a way to just like in general rebalance self-balancing trees inductively, something like that. I just haven't really thought it through. We'll come back to this. I think I kind of want to try to come up with something on my own, but that might be just excessive. Like I might as well just go look and see what do you already do with self-balancing trees to begin with. I probably should do it that way. Yeah, I think that's the way to do it. All right, thank you for watching. I'm actually going to save this. I don't think it's really necessary, but I'm going to save it anyway. This paint picture. We'll just say, which one is this? Leetcode, Reconstruction. I'm not going to give the number. Yeah, I think self-balancing tree concepts, I think I need to review that, and then I probably could come up with something on my own in order to properly balance these trees. But why bother, right? Like, why not just learn about what's already out there, what people already figured out? Because I probably won't come up with anything new, like, realistically speaking, thinking about it. So why should I waste the time? I guess the only reason I might want to spend the time is that, like, kind of uses your brain a little bit, you know, get some practice. I don't know. I'll come back to this. I'll do a little bit of both. I'll spend a little bit of time the next time I look at this. Spend a little bit of time thinking about, like, how to spend a little bit of time thinking about how I might balance my tree, and then I'll look at, like, other self-balancing trees and see, like, how they do it, how it would be done there. I do think at this point in my, I don't know, in terms of my abilities with regard to developing algorithms, I think I would know enough about. I think I would know enough about balancing trees that I could come up with it on my own. I could be wrong too. I don't know. I mean, just the few minutes I thought about it, it didn't get very far. So maybe I'm wrong. Maybe I need to spend quite a bit more time. I don't know. So yeah, thank you for watching. I will talk to you soon. Have a good rest of your day. Do I have anything incriminating on my desktop here? I don't think so. I think we're okay. Yeah. Other than my dad. Yeah, let me go. I'll talk to you soon. Have a good rest of your day. And yeah, take care. Thanks for watching.